Okay, so you are welcome back. Now, let's assume that you are given a equation like this. This is a boost regulator with input voltage 20 volts, and you need to boost it to output voltage of 60 volts. And these are the parameters of the inductor: 450 microhenry. Switching frequency of the switch is 20 kilohertz, and then the capacitor is 220 microfarad. And yeah, so we have this. So with this, you are asked to calculate the duty cycle, and you are asked to calculate the ripple current of the inductor. Okay, delta I of the inductor. Now also here the inductor peak current. Calculate the inductor peak current there. The ripple voltage of the capacitor, the critical values of L and C, and the average and RMS value currents of the switch and the diode. Okay, so now with that, the first thing is, remember your duty cycle equation. Duty cycle is, we say that VO over VS is the same thing as 1 over 1 minus K, right? 1 over 1 minus K. All right, so you just put your values. So we put the values of that. So this implies that VO 60 over 20 equals to 1 over 1 minus K. Okay? So when you make K the subject formula, you'll get 0.667 as K, 0.667. All right? This is 60 over 20, which is 3. Okay? So equals to 1 over K, 1 over 1 minus K. So you can get K to be that. Now the next thing to calculate the ripple current of the inductor. Now how do we do this? So you remember the the voltage across inductor is L change in I over change in time. So if they say you must calculate the ripple, they want us to calculate delta I. So you say delta I, this is now number 2, right? So delta I is VL delta T, all right, divided by L. Remember the T we are talking about is a time of on, right? But now what is time of on is KT, T on, all right? So I'm going to have this to be 450 microfarads times 10 to the power 6. That is, sorry. All right, sorry, made a mistake. Remember what is VL? At time of on, we just switch this on. What is VL? VL is VS, right? So I'm going to write this as VS, which is 20 multiplied by time of on. Time of on is KT, right? KT. So this is KT, and our K is 0.667 multiplied by T. What's our T? The switching frequency. This is the frequency, right? So T, which is a period, is 1 over that times 1 over 20 kilohertz, like that. So divide by the 450 times 10 to the power minus 6. So you just evaluate that. So you get that to be 1.482. So you get 1.482 amps, right? Okay, that is your delta I. All right? That is your delta I. Number 3. So 3 is to calculate the inductor peak current. All right? So let's look at 3. Peak current, I peak, I inductor, peak, which we said, remember, it goes like that. So if I know my I average, and I average is your I in, right? So I have I average plus delta I over 2, okay? Right now, we don't know I average, but I know V in I know P, IO, and the VO. So let's just assume that this is 100% efficient. Power in equals power out. Because I don't know this. I just need to know this. Remember, this is the same as saying I in by plus delta I. Let me just write it here. I in plus delta I over 2. But I don't know I in, but I know I in is the same thing. That is your I in here. I can get it if I said assume. So you assume 100% efficient system. Efficiency. So that means I in V in equals IO VO. So that I in will be equals to IO VO divided by V in, which is our IO there is 2 and VO there is 60 divided by V in there is 20. So I have 2 times 60 divide 20. So you get about 6. So you get 6. That means that this is when I say 6 plus, I take that 1.482 divided by 2. 1.482 divide 2 will give you 0.741. So this will give you 6.741 amps. All right, did you get that? So you get 6.741 amps. The next question is to calculate. The ripple voltage of the capacitor. The capacitor ripple voltage. Okay. So now what do you do in that case? Number 4. What is the current? Remember that the voltage across an inductor, we said is L I dt. But the current charging a capacitor is the same thing as charging a capacitor is C dV dt. Like that, right? You know that. Okay. So what we're saying is IC is C delta V over delta T. So now if they say you must calculate the ripple voltage of a capacitor, they want us to calculate that. Remember, at time of on, when you turn this on, what happens to this current? This current here discharges to the load. That means our IC will be equal to minus IO, right? At time of on, IC will be equal to minus IO. So that means I'm going to write this to be minus IO. I'm using time of on now, right? Minus IO to be this equals to C. Now, delta V is what they want. Divided by which time are we using now? Time of on. And time of on is what? KT. All right, so KT. So that if I now want to get delta V, so I'll say delta V is now the same thing as KTIO minus divided by C, like that. So let's just put the values there. So we have our K, so minus 0.667 times T. Our T is 1 over 20,000 times IO. So our IO is 2 divided by the capacitance, 220 times 10 to the power minus 6. So we just divide that. Let's see. So we get 0.3032 volts. All right. So you get that. So that is how we get 0.303 volts. Now, I think that's all. The ripple voltage. Now, the next thing is just to calculate the critical values of the capacitor. Okay. And remember what we said about critical values? Okay, so now let's start again. So now critical value, we are here at number 5. So let's look at critical value, number 5. So critical value we have that VL is L critical, the I, delta I over delta T. But remember what we said about delta I. All right. Remember that the I, we're dealing with what is happening here. So delta I will now be twice of I in at critical value. So this will be twice of I in. L critical is 2 I in over KT. All right. So here we can now substitute. So the current here now, the ripple will be twice of the average value, right? So that is what we have here, twice of that I in, which is the average value. So now if I want to calculate L critical will now be the same thing as VL KT over 2 I in, right? But remember VL at time of on, because I'm using KT. So at time of on is the same thing as VS. If you on this, VL is VS, okay? So we'll have 20 multiplied by 0.667 times time of on, 1 over that, 1 over 20,000 divided by 2 times I in, and our I in, we got I in somewhere at 6. All right, so let's get the value there. You get about 5.558 times to the power minus 5. All right, which is 55.58, 55.58 micro. What is that? Henry. All right, 55.58 microhenry. Did you get that? Okay, so now the next thing is C critical. Critical value of C. Remember here also, we are going to write IC is C critical by the V over dt. But that V, let's just put delta V, because we're just talking about the ripple now. So delta V over delta T. But that is at time, if I'm looking at time of on, that to be minus 2 for IC that we got somewhere before. IC is minus IO. Let's just put here minus IO equals C critical by delta V will be twice of VO as the average value divided by KT. You have like that, all right? So that if I want to get a critical value, C critical, I'll have KT IO over 2VO, okay? KT IO over 2VO. So we just put the values there. Minus down is 0.667 times 1 over 20,000 times IO is 2 divided by 2 by VO, 60. So we have, so you get 5.558 times 10 to the power minus 7, 1, 2, which is 555.8 times the power minus 9. That is 555.8 nanofarad. Okay, as the critical value. All right, so get that as critical value. Now, the last thing that we just need to do is this, to calculate the average and RMS current of the switch and the diode. Okay, the average and RMS current of the diode. So remember that for you to solve this, Let's just clean here. Remember how the average value, the signal of the current flowing through the switch and the diode looks like. Current flowing through this switch, it looks the same way as that of that. Remember, it goes like that at time of on, so this builds up, and that's all. At time of off, if we switch off, there's no current flowing through there. All right, so you only have that. So this goes up, and that's all. All right. So, and you know what this peak value is? It is the same peak value as that of the peak value of an inductor. So if you find the average value of that, okay, of that signal, we're not going to prove it now, but IT average will be the same thing as Ki in. So IT is K. If you find the average value of this signal, okay, it will give you, remember that it's this signal like that with respect to the whole period, because it goes like that. So you must get from here to there. So our I in, K is 0.667 times I in times 6, 4.002 amps. Now the same thing with the same signal, you can easily calculate the RMS value also. RMS value of that IT RMS is square root of K by I in. Okay, so just find root K by I in, the square root of 0.667 times 6. Okay, amps, 4.9 amps. All right. So that is for the switch. The diode, how does a diode signal look like? Look, remember that when this is off, when this is on, only this goes, nothing goes to the diode. So on the diode side, when this is on, this is off now, the current here that was built up begin to discharge. So you are still going to have, remember how it looks like at this point. It needs to discharge like that, okay, until you get to a particular point, like that. So now you just need to know what will be the average value of that, okay? And the average value for the diode is 1 minus Ki in, okay? I diode 1 minus K I in. ID RMS will now be the square root of 1 minus K I in. So you can just put the values there. All right, so we put the values there, all right, as 1 minus 0.667 times 6, and this one will be 1 minus 0.667, the square root, times 6. Okay? 1.998, 3.462 amps. All right? Did you get the problem? Did you get that solution? Okay? If you don't understand anything, play back the video and then try to get it right. Okay? All right? Thank you very much. Okay?